Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 4 of algebraic topology. In our previous lecture, we discussed what is homotopy and how it is an equivalence relation. In this lecture, we will continue with our discussion of homotopy, and we will discuss what is a homotopy category. And in the second part of our today's lecture, we will discuss what is a quotient topology. So far we have learned that homotopy is an equivalence relation on the set of all continuous maps. So what is an equivalence relation? So we proved that it is a reflexive. So reflexive means f is homotopic to itself, and it is symmetric. So symmetric means if f is homotopic to G, then this implies G is homotopic to f. And thirdly, it is transitive, which means if f is homotopic to G and if G is homotopic to H, then this implies f is homotopic to H. So this form equivalence relation. So we already know that if we have an equivalence relation, then this gives us equivalence classes. So what is an equivalence class? So for example, if we have a continuous function from x to y, then its equivalence class is basically set of all continuous functions from x to y which are homotopic to G. So the family of all such homotopic classes is denoted by x to y. So what is this set x y bracket? So basically this will be the collection of homotopy equivalence classes of functions. So for example, it will be a set of the following form. Okay, so where this square bracket f1 is basically homotopy class of f1, this is homotopy class of f2, this is homotopy class of f3. So basically this bracket x to y is basically collection of all homotopy classes of continuous functions from x to y. So we already know that what is home in the category of top from x to y. So if x and y are topological spaces, then they belong to the category top, so the category of all topological spaces. So what is home from x to y? So this is collection of all continuous functions. So f such that f from x to y is continuous. So now what's the difference between home and this square bracket x to y? So this is collection of all continuous function, but this square bracket x to y is basically collection of all homotopy classes of continuous functions. So basically you can just say that this has relatively less elements than this, because it has homotopy classes. So this one element contains many elements, so all continuous functions which are homotopic to f1. And similarly this set, this equivalence class contain all continuous functions which are homotopic to f2 and up to so on, but this set contains all continuous functions from x to y. So next we have an important result. So this result says that if f naught is homotopic to f1, what is f naught and f1? So f naught and f1 are continuous functions from x to y. And if we have g naught homotopic to g1, so what is g naught and g1? These are continuous functions from x to y. So if this happens, then g naught composition with f naught is homotopic to g1 composition with f1. So we have to prove this thing. So of course, if g naught composition f naught is homotopic to g1 composition f1, then they have the same homotopy class. So this result says that if I have homotopy class of f naught, then I can compose this homotopy class with g naught and this is equal to the homotopy class of F naught composition G naught. So this homotopy class is not just one element, it's a class, so it has many elements. So if I replace this F naught with some other element of this class, for example F1, which is homotopic to F naught, so let's replace this F naught with F1. Of course these two classes are the same, so these two elements are the same because F naught has the same homotopy class as F1. And if I compose this with some other element G1, okay, so this G1 is basically homotopic to G naught. Okay, so once again this is a homotopy class and this is equal to this class, so as a class they are equal, so they are equal elements. Similarly these are equal elements because both of these elements G0 and G1 represent the same class. So the homotopy class set of all continuous functions homotopic to G0 or set of all continuous functions homotopic to G1, so it's the same class. Okay, so this is equal to F1 composition G1 or the other way around. Okay, so let's prove this result which will provide us a background so that we can compose any two equivalence classes. Okay, so let's see how to prove this result. So the proof of this result is in two steps. So in step 1 we will show that G0 composition F0 is homotopic to G1 composition F0, and in the second step we will show that, so in the step 2 we will show that G1 composition F0 is homotopic to G1 composition F1. So basically we need a map. Okay, so let's define a map H of xt from x cross I, so where I is closed interval 0 to 1 to y. Okay, so let's assume that F is homotopy from F0 to F1 and G is homotopy from G0 to G1. Okay, using F and G let's define this H of xt in the following way, so is equal to G of F0 of xt. Okay, so since G is continuous, so that's why H is also continuous. So let's see what is H of x0. So G of whatever this value of x is, and if we take t is equal to 0, then we will get G0. So basically this is equal to G0 of whatever this value of x is, so in this case it is F0 of x, so which is equal to G0 composition F0 at point x. So in other words H of x0 is G0 composition F0. So now let's see what is H of x1. So this is equal to G of F0 of x at t is equal to 1. So since G is homotopy from G0 to G1, so for t is equal to 1 we should get G1. Okay, so this is equal to G1 of whatever this value of x is, so in this case it is F0 of x, so which is equal to G1 composition F0 of x. So in other words H of x0 is G0 composition F0, H of x1 is G1 composition F0. So and H is also continuous because G is continuous. So we have a function from x cross I to y satisfying the properties of homotopy. So this implies that G0 composition F0 is homotopic to G1 composition F0. Okay, so that's the step number 1. So let's see how we can show that G1 composition F0 is homotopic to G1 composition F1. So for that we need a function k of xt from x cross I to y. Okay, so we define this k of xt in the following way. So this is equal to G1 composition of f of xt. So in other words, we are just saying that this is going to be equal to G1 of f of xt. So of course G1 is continuous and f of xt is continuous, so their composition is continuous, because we know that composition of two continuous functions is a continuous function. So let's see what is k of x0. Okay, so this is the definition of k of xt. So using this definition, k of x0 is equal to G1 of f of x0, so which is equal to G1. So what is f of x0? So f is homotopy from f0 to f1, so f of x0 is f0. Okay, so this is equal to f0 of x, so which is equal to G1 composition f0 of x. Okay, similarly let's see what is k of x1. So basically this is equal to G1 of f of x0, sorry, f of x1, so which is equal to G1. So what is f of x1? So f of x1 should be equal to f1, because f is homotopy from f0 to f1, so this is equal to f1 of x, so which is equal to G1 composition f1 of x. So here we can see that k of xt, which is a continuous function, and k of x0 is G1 composition f0, and k of x1 is G1 composition f1, so which proves that G1 composition f0 is homotopic to G1 composition f1. And we also know that homotopy is transitive. So in other words, if G0, so in other words, if G0 composition f0 is homotopic to G1 composition f0, so this and G1 composition f0, which is the same as this function, is homotopic to G1 composition f0, so this implies that this function is homotopic to this function. Okay, so hence this implies that G0 composition f0 is homotopic to G1 composition f1. So this is the end of the proof. Let's recall some properties of the category. So a congruence on a category is an equivalence relation on the class, or basically this class, which is union of all homomorphisms from A to B, and A, B are basically objects of this category. So A and B belongs to the objects of the category. Okay, so such that the following conditions are satisfied. If f is an element of home A to B and f is equivalent to f prime, then f prime is also element of home A to B. And the second condition is if f is equivalent to f prime and g is equivalent to g prime, then g composition f is equivalent to g prime composition f prime. In other words, this equivalence relation respects the operation of composition. So if these two conditions are satisfied, then we say that this equivalence relation is a congruence on the category C. So if we have a congruence on the category C, then we can define the quotient category. So what is a quotient category? So in the quotient category, objects of C prime and C are the same. So where C prime is the quotient category. So objects are the same and this homomorphisms. So there is a change in this set of home. So how do we change? So basically in place of just homomorphisms from A to B, we replace them with their equivalence classes. So now the elements are not just elements, they are equivalence classes. Okay, so of course the number of homomorphisms in this category C prime is relatively less than the number of morphisms in the category C, because in category C we are just taking homomorphisms from A to B, but in the category C prime we are taking their equivalence classes, and equivalence classes may have many elements. And the third property, of course, we know that a category has three important components: objects, homomorphisms, and the composition. So how do we compose these? So the equivalence class of G composed with equivalence class of F is equal to G composition F, and this is well defined because if G is congruent to G prime and F is congruent to F prime, then this condition says that G composition F is congruent to G prime composition F prime. In other words, if I have equivalence class G and if I am composing this with equivalence class F, then this is equal to equivalence class of G composition F. So I can replace this G with any other element of this equivalence class. Of course, if I take another element of this equivalence class, then it will be representing the same class. So and similarly, if I replace this F with another element of this equivalence class, then because they are representing the same class, so I should be able to compose this, and as equivalence classes, these two, the equivalence class of G and equivalence class of G prime, are same because G is equivalent to G prime. Okay. Similarly, F, the equivalence class of F, and equivalence class of F prime are the same because F is equivalent to F prime. So this is equal to, of course, G prime composition F prime. But since we impose this condition that G composition F is equivalent to G prime composition, sorry, this should be composition, so G prime composition F prime, so so these two elements, G prime composition F prime is equal to G composition F, so these two elements are congruent, so that's why their equivalence classes are the same, so these two are equal, so that's why we can define this composition. Okay, so this new category, which has the same number of objects as or which has the same objects as the category C, but the morphisms are different. Instead of morphisms, we are taking their equivalence classes, and composition is defined in this way and is well defined due to our conditions on the congruence. So this category is called the quotient category. So this is just a recall from our previous discussion. So I'm sure most of us can see the similarity between this discussion and the discussion of the homotopy. So we know that homotopy is an equivalence relation on the set of all continuous maps from X to Y, and similarly we can consider a set of all continuous functions. So we can consider hom X t where X t belongs to the category of topological spaces. So top is basically the category of all topological spaces where morphisms are continuous functions and the composition is usual composition. So we can define this equivalence relation of homotopy on this set, and it also satisfies the two properties. So what are the two properties? So it satisfies that if F is equivalent to F prime, that F prime is also homomorphism from B to A, and this composition property. So both of these properties are satisfied by our homotopy. So we also proved this and we also proved this. Okay, so with these two properties we can say that homotopy is a congruence on the category top. Okay, so of course we can define a quotient category then, and this quotient category is called homotopy category and is denoted by H top. So let's see again what are the objects of this homotopy category. So the objects of this H top are the same as the objects of top. So the objects are just topological spaces. So what are the objects of top? Set of all topological spaces. In fact, class of all topological spaces. So what are the morphisms? So hom from X to Y in this category of H top. So this is basically equal to equivalence classes. So this equivalence class is under the equivalence relation of homotopy, okay, such that f from x to y is continuous, or we can say that f belongs to home in the category of top from x to y. So instead of taking just morphisms from x to y, and again if we are taking the category of topological spaces, this morphism means it's a continuous function. Okay, so instead of taking these morphisms, we are taking their equivalence class. Okay, and similarly we can compose two equivalence classes, and the composition is defined in the following way. So f composition G, and according to this result which we just proved, this composition is well defined. So let me say again why this is well defined, because if f is homotopic to f1 and G is homotopic to G1, then the composition of these two homotopic classes is equal to f composition G, because if I replace this f with any other element of this class, for example f1, then this composition, and if I replace this G with any other element of this class, let's say G1, then this is equal to f1 composition G1. But according to this result, this is homotopic to f composition G, and so these two classes are equal. So I can replace an element with any other element of the class. Of course they are representing the same class. So in other words, what I'm just trying to say is this equivalence class is equal to this equivalence class, because f is homotopic to f1. So as a classes they are equal, and we can choose any element of the class to represent that class. And similarly the equivalence class of G is equal to the equivalence class of G1, because due to the properties, or due to the fact that homotopy is equivalence relation, if G is homotopy to G1 and G1 is homotopy to G1, then G2, then G is homotopy to G2. So due to these properties, I can take any of the element of this class to represent this element. So f1, so these two elements are same as classes, and these two elements are same as classes. So I should be able to represent this class with any element that I want. So if I replace f with f1 and G with G1, then still their compositions are equal. So composition is well defined. So now we have this new category of homotopy category, where the objects are the same as the objects of top, and morphisms are defined in this way, and composition is defined in this way. And we already know that there are only three important or three main components of category. Okay, so we have objects, we have morphisms, and we have composition. Okay. So why do we need this new quotient category of top, namely the homotopy category? Okay, so this is needed because in algebraic topology we'll be associating our topological spaces with some algebraic structures, so for example groups and other objects. So if we have a functor T from the category top to some category A, so where A is any algebraic category, for example category of abelian groups, category of groups, and category of rings, etc, etc, etc. So if we take A to be any algebraic category, and this input category is basically a category of topological spaces, and this is a functor. So let me remind you what is a functor. So functor takes images of objects and also takes images of maps, and it respects the composition, and it takes identity functions to identity functions. Okay, so with these four properties we have this functor. Okay, so if we have this any functor from the category of top to some algebraic category, then it satisfies the following property. So if f is homotopic to G, and f and G are basically morphisms from A to B, and A or B are topological spaces. So morphism means they are continuous functions in this case, in the category of topological spaces. And if f and G are homotopic, then we have T of f is equal to t of g, which is a very important property. So what we are saying is, if two functions are homotopic, if two continuous functions are homotopic, then their image under this functor, they are the same. Okay, so we don't need to take all morphisms from A to B, and what we need is, we just need to consider the equivalence classes under the homotopy. Okay, because then we will be considering some extra elements that we don't need. Okay, so this makes our problems of algebraic topology easier, because if maps are homotopic, then their associated algebraic maps are same. So if I just take T from H top, then it will be much easier. So why it is easier? Because H top has much less morphisms, because it takes equivalence classes of functions and not just functions. So what are the equivalences in H top? So we know that, let's recall what is an equivalence in a category. So an equivalence in a category C is a morphism F from A to B, for which there exists a morphism G from B to A, such that their compositions, their two different compositions are identities. Okay, so let's see, H top is a category, the quotient category of top, and what are the equivalences in this category? So a continuous map F from X to Y is homotopy equivalence if there exists a continuous map G from Y to X, such that G composition F is homotopic to 1x and F composition G is homotopic to 1y. Two spaces have the same homotopy type if there is a homotopy equivalence X to Y. So we say that two spaces X and Y have the same homotopy type if there exists a function F from X to Y and there exists a function G from Y to X, such that G composition F is homotopic to 1x and F composition G is homotopic to 1y. Okay, so in the category of H top, or in the language of H top, we can say that a function is homotopy equivalence if the equivalence class of F, which belongs to, of course, XY bracket, which means the collection of all homotopy classes from X to Y, is an equivalence in H top. Of course, this is a category, and what is an equivalence in a category? So equivalence in category means that if we have a function, okay, so of course F is a function from X to Y, then we have another function G from Y to X, okay, and so in this category the morphisms are equivalence classes under the homotopy. So the elements of H top are basically, the morphisms of H top are basically the homotopy class of F and homotopy class of G. So we can take their composition, so F composition G, so this should be equal to the homotopy class of 1y. Of course, when we are saying they are equal, it means, okay, so this side is equal to F composition G equal 1y. So when we are saying equal, it means F composition G is homotopic to 1y, because these two equivalence classes are equal if and only if F composition G is homotopic to 1y. So if and only if F composition G is homotopic to 1y. So in H top we can say that F equivalence class composition G equivalence class is equal to the equivalence class of 1y, and similarly we say that G equivalence class composition F equivalence class is equal to the equivalence class of 1x. So in H top, in the homotopy category, so that's how we define these things. So that's how these two definitions are equivalent definitions. So homeomorphic spaces have the same homotopy type. So if X is homeomorphic to Y, it means that there exists a continuous function F f is bijective. Also we have another function f inverse from y to x such that f composition f inverse is equal to f inverse composition f is equal to identity. Okay, so now we know that f of x is homotopic to f of x, because homotopy is an equivalence relation and equivalence relation is reflexive. So let's see how they are homotopic. So I can define a function x cross I to y given in the way that f of x t is equal to f of x. So which means that f of x 0 is also f of x, and f of x 1 is also f of x. So we can say that if we have same function, if f of x is equal to f of x, then they are homotopic. Okay, so from this we can say that f composition f inverse is homotopic to 1 and f inverse composition f is homotopic to 1. So of course f composition f inverse is homotopic to 1y and f inverse composition f is homotopic to 1x, because they are equal and the equal functions are homotopic. So in this way we can say that x and y have the same homotopy type. So our next definition is null homotopic. If x and y are spaces and if y naught belongs to y, the constant map at y naught is the function c of x is going to y, defined in this way. So for example, if I have space x and if I have some other space y, and y naught is some point of y, then a map which takes each and every point of x to y naught. Okay, so it's taking every point of x to this point y naught. Okay, so this is a constant function. A map f from x to y is null homotopic if there exists a constant map c from x to y with f homotopic to c. Okay, so if I have some other function, let's say f which takes x to some subset, okay, so let's say this subset, okay, so it takes the whole of x to this subset. So this is the image of f, so this is f of x. Okay, so if this f of x is homotopic to this c of x, so in other words we are saying that there is a homotopy which continuously deforms all of this f of x to y naught. So it takes each and every element of f of x and under some continuous map everything is just going to this point y naught. Okay, so null homotopic, a function f is null homotopic if there exists a constant map c from x to y with f homotopic to c. So using the idea of null homotopic we can prove fundamental theorem of algebra, which states that every non-constant complex polynomial has a complex root. Of course this means that every degree n complex polynomial has exactly n complex roots. So these two are equivalent statements. So we can use this idea of null homotopy and we can prove fundamental theorem of algebra, but we are going to exclude the proof of this result. Contractible. A space X is contractible if one X is null homotopic. Okay, so once again what is identity function? So identity function takes let's say this is space X and this takes each point of X to itself. Okay, so this whole X is the image of the identity function. Null homotopic means there is a point x naught, and there is a continuous deformation of this image to this point x naught. Okay, so there exists some f from x cross I to x such that f of x0 is equal to identity function and f of x1 is equal to this constant function. So what is this constant function? Taking every point to x0 for all x belongs to capital X. So there exists this homotopy, so which means that it takes this function, which is identity function, and the images of this identity function is the whole space X, and what are the images of f of x1, which is the constant map, is just this point this. So with the passage of time, so when I'm saying time, it means when I'm varying these values from 0 to 1. So starting from 0, I am having all points of the space X, and with the passage of time, I am contracting the thing, contracting the space X to this point. So that's why we say that a space X is contractible if one X is null homotopic. Every convex set is contractible. Okay, so let's see how every convex set is contractible. So the idea is very simple. So what do we need to show? We need to show that identity, which is a function from x to x, defined in the way that 1 of x is equal to x for all x belongs to capital X. Okay, and it is contractible, which means one x should be null homotopic to a constant map. So what is a constant map? So let's say a constant map is x naught, where x naught is some point, okay, for all x belongs to x, and x naught is some point of capital X. So now we need to show that there exists a homotopy from 1x to c of x. So let's define f of xt in the following way. So t x naught plus 1 minus t x. Of course, this is a continuous function because the only variable here is x, and for each and every value of the parameter t, it's a continuous function. Okay, so what is f of x 0? So when I take the value t is equal to 0, so this becomes 0, and this is equal to x, so which means this is equal to 1x of x. So similarly, let's see what is f of x1. So for x is equal to 1, this is 0, and this becomes x naught, so which is basically equal to c of x. So it is a continuous function which satisfies these two properties. So we can say that this f is homotopy from 1x to cx, and which means that 1x is homotopic to a constant function, or in other words, we can say that this space is contractible. So let's see what is the definition of null homotopic again. So we say that a continuous function is null homotopic if f is homotopic to c, and a space is contractible if 1x is null homotopic. Okay, so according to the definition of contractible, this convex set X is contractible. So what's the basic idea that we are trying to use? So basically what we are trying to use is take any point of the space X and draw a line segment from x naught to x, and with the passage of time t, you move from that point x to the point x naught. So if I have a point x of this space, then there is a line segment joining this point and x naught, and for t is equal to 0 we have this position, and for t is equal to 1 at the end of our time interval we are at point x naught. So we can take any other point and we are moving along these segments to the point, and take any other point, take any other point. So we are moving along these line segments and we are moving to this point, x naught. So we are contracting the space. So if 1x is null homotopic, or in other words 1x is homotopic to a constant map, so that's why the space x is called contractible, because we can contract each and every point. We can contract the whole space to just one point. Okay. So the converse of above theorem is not true, as a hemisphere is not convex. So we know that a hemisphere is not convex, because if I have any 2 points on a hemisphere, then the line segment joining them is not totally contained in the hemisphere. So the only points contained in the hemisphere are these two endpoints, and the line joining them is not contained on the surface of the hemisphere. So that's why hemisphere is not a convex set, but it is contractible. So we can define a homotopy which will take 1x, and it will be homotopic to a constant function. So that's why this hemisphere is contractible. Similarly, we see that this n sphere Sn is neither convex nor contractible. So the only result in this case is the convex sets are contractible, and there is no apparent general relationship between convexity and contractibility. A space X has the same homotopy type as a point if and only if X is contractible. So a space X has the same homotopy type as a point. So when we say that space X has same homotopy type as a point, it means that there exists a function f from X to a point, and there exists a function g from point to X such that f composition G is homotopic to 1A, the identity of A, and G composition F is homotopic to 1X. Okay, so that's what it means, that space X has the same homotopy type as a point. Now we have to show that, so now we are doing the first side of the proof. So we have to show that X is contractible. X is contractible. So if we want to show that X is contractible, so we need to show that, we need to show that 1x from X to X is homotopic to a constant function. Okay, so let's consider this part of the given data. So what is G composition F? So applied on any element of X, this is equal to G of F of X. So F of X is some point, but here G is basically a constant function. So this is equal to G of A, and G of A is basically A. So basically this G composition F is a constant function. So because for each and every small x belongs to capital X, the image is A. So also it is given that G composition F, which is a constant function, is homotopic to 1x, so which is the identity map, and that's exactly what we needed to show, that 1x is homotopic to a constant function. So this implies that X is contractible. So let's show the converse part. So conversely, let X is contractible. So if X is contractible, which means that 1x is null homotopic to some constant function, so where k of x is equal to x naught. Okay, so where x naught is some point of capital X. So this is the given data. Now what do we need to show? So to show is there exists f from x to x naught and g from x naught to x such that f composition G is homotopic to 1 x naught and G composition F is homotopic to 1 x. So that's what we need to show here. So define f of x is equal to x naught and define G of x naught is equal to x naught. Okay, so now we need to show these two things. So what is f composition G? So f composition G of x naught is equal to f of G of x naught, which is equal to x naught, and f of x naught is equal to x naught. So which means that this is equal to identity. Okay, so this implies that f composition G is equal to identity on x naught. Of course, if two functions are equal, then they are homotopic. Now let's see what is G composition F of x. Okay, so this is equal to G of f of x, and which is equal to G of x naught, and which is equal to x naught. So basically this is the same as, so this implies that G composition F is the same function as our function k of x. Okay, so basically this is equal to k, but then we also know that k is homotopic to 1, so this implies that G composition F is homotopic to 1x. So that's what we needed to show. Okay, so these two things are shown, so we can say that this space X has the same homotopy type as a point. So we have proved that X has the same homotopy type as a point if and only if X is contractible. So our next result is if Y is contractible, which means that one Y is null homotopic to a constant map, then any two maps are homotopic. Okay, so let's see how to show this result. So the given data is Y is contractible. So contractible means that one Y is null homotopic to a constant function. So we take constant function to be C of Y is equal to Y naught for all Y belongs to capital Y. So this is the given data. So what is to show? So to show is if I have any two maps from X to Y, then they are homotopic. So in particular, I take one map to be G of X is equal to Y naught for all X belongs to capital X, and I take the second function to be any continuous function from X to Y. So if I can show that any continuous function from X to Y is homotopic to this G of X, then since homotopy is an equivalence relation, so every two continuous functions from X to Y are homotopic. So let's see how to show this result. So we have a continuous function from X to Y, and from Y to Y we have two functions. So one function is the identity function, and the second function is our function C, and also one Y is homotopic to C because Y is contractible. Okay, so now I can write down this F to be equal to 1Y composition F. Of course I can do that because F of X is the same as 1 of Y F of X, because it is an identity function, so it must be equal to F of X. So identity function takes any value to itself, and F of X is a point of Y. So this is homotopic to C, because 1 is homotopic to C composition F. So basically we are using the following property of the homotopy. If F is, let's say F naught is homotopic to F1, G naught is homotopic to G1, then F naught composition G naught is homotopic to F1 composition G1. So basically using this property we can say that 1 is homotopic to C, F is homotopic to F because homotopic is reflexive. So 1 composition F is homotopic to C composition F. So what is C composition F? So let's see what is C composition F. C composition F starting from X, so this is equal to C of F of X. So it takes elements of capital X as the domain, and the output is basically Y naught. So it is basically the same as our function G, because the domain of G is X and the output is always Y, so it is equal to Y. So basically we can say that F is homotopic to G. So this implies F is homotopic to G. So since F is basically homotopic to a constant function, so we can observe that G is a constant function. So we can say that F is null homotopic, and F is any continuous function from X to Y. So we can say that any continuous function from a space X to a contractible space is null homotopic. Okay, so that's the end of the proof. Our next topic is quotient topology. So how do we define quotient topology? So if X is any topological space, then and if we have X prime, which is the collection of subsets of X which are disjoint, and also its union is equal to the whole space X. Of course this is called a partition of X. So the natural map V from X to X prime defined by V of X is equal to Xj, where Xj is the unique subset in the partition containing X. So basically what we are doing is, let's say this is my space X. I'm partitioning this space. Okay, so partition this space. So this is my space X1, X2, X3, X4, X5, X6, X7, X8, X9. So in this case there are 9 elements. So what is X prime? So X prime is equal to X1, X2 up to X9. Okay, so we can see that their intersection is always empty, and their union, so if I take the union of all these Xi's where I is equal to 1 to 7, this is equal to X. So now we define a map from X to X prime. Okay, so defined in the following way: V of X is equal to Xj. So let's say I take an element X. Okay, so this is a point X of the topological space capital X. Now what is V of X? So in this particular case it's going to be X4, because X4 is the unique element. So we can observe that this X will belong to only one of these sets of the partition. Okay, so because if it belongs to more than one sets, then the intersection of these Xi's will not be empty. So X belongs to only one element, and that element is basically the image of this X under this map V. And similarly, let's say there is another element Y, so V of Y is equal to X9. Similarly, if I have another element, let's say Z, then V of Z is equal to X3. So that's how we define this map. So the quotient topology on X prime. Okay, so what is X prime now? So X prime is basically these 9 elements. So our space is basically very much reduced. So in this particular case, it's been reduced from this topological space X to only these 9 elements. So in this quotient topology, so what are the basically open sets? So the quotient topology on X prime is the family of all subsets U prime of X prime for which V inverse of U prime is open in X. So basically all subsets of X prime. So for example, if I have X1, so if the inverse image of U, so in this case X prime under this map V If it's open in X, then we say that it is open in X prime. Okay, so that's how we define quotient topology. So for quotient topology, we need two basic ingredients. So I need a partition on the space X, I need a map V from X to X prime. So using this map, we can define what are the open sets. So as a particular case, let's consider a topological space and a subset A of the topological space X. So we can construct a partition on X in the following way. So construct this X prime as, so take this A as one set and take all the singletons of the complement. Okay, so basically if we have this topological space X and let's say this is the set A, so what we have done is taken this set as one element, and in the rest of the space in X minus A, take all the elements and make them into singletons and make them into basically sets. So this is basically a partition. Of course, if I have one point and another point, then of course let's say this is X1 and this is X2, then the intersection X1 X2 is always empty, and their union, because this is the collection of all points, so their union union A is definitely equal to X. So this is a very particular case of the quotient topology, where we are taking this very particular partition of the topological space X. So in this case, this subset A becomes a point of the quotient topology, because what are the points of X prime? So the subsets of X. So in this case, this one subset is one point, and the other points remains the points. Okay, so we denote such quotient topology by X by A. So in particular, let's say X is equal to 0 to 1 open interval, and A is just 2 points. So basically, what is the space X? 0, 1 open interval, and A is 0, 1. So basically, these 2 points is my set A. So the quotient space. So in the quotient space X prime, what are the points? So 0, 1 union the points, the singletons. So where X are points from 0 to 1, but not 0 and 1, because 0 and 1 is already here. Okay, so now this set A is 1 point. So in other words, we can say that this 0 and 1 are equal in our quotient topology. So 0 and 1 are the same points. So the same point in our quotient topology. Of course, we can define what is V in this case as well, but the point is we are identifying this 0 and 1 because it's the same point in my new topological space. So basically, we can say that this new space behaves like a circle. Okay, so intuitively it's a circle. So basically, we have taken quotient of an interval 0 to 1, and we identified these 2 points, this 0 and 1. So after their identification in this way, in the quotient topology, it becomes a circle. Let's consider another special case of a quotient topology. So in this special case, we partition the topological space by using an equivalence relation, because in the quotient topology we need 2 things. So one is the partition of the space, and the second thing is a map V from X to X prime. So in this case, we take X prime to be the equivalence classes of this equivalence relation, and the map V from X to X prime is defined in this way. So take X and take the image of X to be its equivalence class. So this gives a quotient topology, and we denote such quotient topology by X by tilde. So let's take, for example, X to be I cross I, where I is equal to 0 to 1. So basically, this is this square in our plane. So let's say this is my x-axis and this is y-axis, and this is 0, this is 1, and this is 1. So this square is basically my topological space X. So define equivalence relation on X as, so x0 is equivalent to x1. Okay, so take any x and the value of y is basically 0. It's equivalent to take any x and the value of y should be 1. So for example, if I take one point from here, so take this point, this is the point x0, so this is equivalent to, this is the point x1 on the same line. Okay, so this is equivalent to this. Similarly, this point is equivalent to this point, and this point is equivalent to this point, and this point is equivalent to this point. So basically in the equivalence relation, so in the equivalence class of x0 there are 2 points. So x0, sorry, the ordered pair x0 and the ordered pair x1. So this is the equivalence class of x0. Similarly, what is the equivalence class of some other point x1, which is of course the same as x0 and x1. So in my new quotient topology, this is one element. In other words, I have identified this x0 with this x1. I have identified this point with this point. I have identified this point with this point, and this point with this point, and up to so on. So for each and every value of x, I have identified all of these points with their corresponding points on this side. So in other words, we can say that I'm joining this line with this line, and it basically becomes a cylinder. Okay, so something like this. Okay, so if I join this point with this line, then it basically becomes a cylinder from 0 to 1. Okay, so we can say that this quotient topology is homeomorphic to a cylinder, because I am identifying points of this line with the points of this line. Now let's go one step further in this example. So let's consider X to be the same topological space, but change this equivalence relation in the following way. So now once again we have this square. x0 is the same as x1, so in other words, I am identifying this line with this line. Okay, so these two lines are same. Also, there is an extra thing added here. So 0y is the same as 1y. So this line is the same as this line. So in the quotient topology, so similar to the previous case, in the quotient topology, we first identify this line with this line, and then identify this line with this line. Okay, so in the first case, after identifying this line with this line, it becomes a cylinder. Okay, so it becomes this thing. So this is step 1. So in the step 2, when we identify this line with this line, so now these two lines are basically this. So these are the two lines. So we are identifying them. So in other words, we are trying to form something like this. So it's basically a torus. Okay, so in this case, it becomes a torus. So if you join this with this circle, then basically it becomes torus in step 2. So after taking quotient of the space X, we get a space which is homeomorphic to a torus. So cone over a space, if X is a space, we define an equivalence relation on X cross I. So basically, if this is my space X, and I is basically 0 to 1 interval, so taking their cross product will give me something like this. So this is the space, and for each and every value, so basically this is the line 0 to 1, so this is the t line. So for each and every value of t, I have space X. Okay, so now I am defining an equivalence relation on this space X cross I. So what's the equivalence relation? So xt is equivalent to x prime t prime if t is equal to t prime is equal to 1. So any 2 points are equivalent if t is equal to t prime is equal to 1. So in other words, so when t is equal to t prime is equal to 1, so basically on this part, okay, so on this part the value of t is 1. So in other words, if I take any point on this level at t is equal to 1, so any point on this level, they are equivalent. So in other words, what we are saying that in this new quotient topology, this whole level where t is equal to 1, this whole new thing at t is equal to 1, this becomes just one point of my quotient topology. So basically, if you take this as one point, then in the quotient topology this is something like this, and t varies from 0 to 1, and basically the space becomes something like this. Okay, so we can observe that this is very similar to a cone. So that's why we say that for any space x and on x cross I, if we define this equivalence relation, and in this equivalence relation we have this quotient space. Okay, so this quotient space is basically a cone, and what is this vertex? So where t is equal to 1, so this is x1. So this is an equivalence class under this equivalence relation. So of course x1 is the same as x prime 1, where x prime is any other element of the topological space x. But since in the quotient space this is an equivalence relation, and this equivalence relation, so this equivalence class is just one point, so that's why it's just one point. For every space x, the cone Cx is contractible. Okay, so very important result, but the proof is very simple. So we have a space x and the cone Cx, we have to show that it's contractible. In other words, we have to show that 1x, which is identity function from Cx to Cx, of course defined by so xt, because the elements of Cx are xt. Okay, so this is equal to xt. We have to show that this is basically homotopic to a constant function. So in particular the constant function that we take is basically cxt goes to x1. Okay, so now we need to find a function from Cx cross I to Cx. Okay, so let's define this function xt s in the following way. Okay, so basically this s belongs to this interval I. So in this case we are using a different name of the parameter s. Okay, so let's define this in the following way. So this is equal to x1 minus s t plus s. Okay, so we can see that for s is equal to 0, okay, for s is equal to 0 we have equal to xt, so which means this is equal to identity of Cx, and for s is equal to 1 we have this is equal to x, and so for s is equal to 1, so this becomes 1 minus s plus s, which is equal to x1. So of course this is equal to the constant function, because the image of every xt is equal to x1, and this function is also continuous, so we can say that 1 Cx is homotopic to C, so which means that Cx is contractible. So note that so note that this x, there is no condition on this x, so take any x, so the cone is contractible, and what's the point of contraction? So the point of contraction is this vertex, so this vertex, so we can contract this whole space, so this whole cone over any topological space x to this one point. Okay, so point of the space is contracted to this vertex. So next time we will be interested in path connectedness. This is the end of the lecture. So before ending the lecture, we can see that we have this polygon, and we can define a quotient topology of this as well. So identify this with this, identify this side with this side, identify this side with this side, and identify this side with this side, and the shape that you will get is basically this. So if you have this topological space, then its quotient topology is something like this. So this is the end of the lecture. Thank you very much, and Allah Hafiz.